So, hello everyone, good morning. I'm Akshay Patil. I'm currently a master student at Quantum Technology in the IIP department. So, before I'd like to introduce Professor Chandni. For the conclave talk. So, she is the one beginning the conclave talk. Okay. So, she obtained her MS and PhD in physics from IISc Bangalore in 2008 and 2012, respectively. She was employed as an IQIM postdoctoral scholar at Indian Institute of Science for Quantum Information and Matter, California Institute of Technology, USA, and also at Jawaharlal Nehru postdoctoral visit as a visiting scientist at Tata Institute for fundamental research, Mumbai. She also joined the department. So she is currently working at IIP department in the nanoscale devices and fabrication lab. I'd like to invite her. For the talk. Thank you.
Okay. Good morning, everyone, and thanks to Akshay Naik and Akshay Singh for the introductions, and thanks to Quantum Research Park for giving me this opportunity to briefly discuss about our work in a very broad sense. So as was introduced, I'm a faculty member in the Department of Instrumentation and Applied Physics, and my lab, we focus on working with 2D materials. I'm a physicist by training, and we do the quantum materials aspect that Akshay was mentioning about. So in today's talk, I'll briefly discuss about what is a 2D material. Since the audience is very broad, and I'll try to keep the talk quite basic. I'll discuss about what are the opportunities that 2D materials provide us, and how this talk has got this word magic over here. So what I mean by this magic, and how we can connect possibly to various quantum technologies that are coming up these days. So what you see on the screen here, there are two graphene layers. You are probably familiar with what is graphene. It's a single layer of graphite, and they're rotated with respect to each other. And there are these nice patterns that emerge. So there is this, what is called as a super lattice. So there's this larger, a repeated unit that appears, and that's what my lab has been focusing on the last few years. We'll come to that towards the end of the talk. But to begin with, I'll go very slow and very basic. So let's talk about what is 2D flatland, right? You may have heard of this word, but what does it actually mean? So this is fairly simple, that when you have a three-dimensional structure, you have basically three axes that you talk about. And when it's 2D, you're talking about something that's confined in a plane. Okay, now why are we interested in this, right? So let's say these objects, they're sort of identical with one of these dimensions reduced to 0. But when it comes to 2D materials, that's not exactly what happens. So let's say that I take an apple and I cut it into pieces, right? So you expect that you have small slices of apple, which tastes like apple, looks like apple, in all sense it's an apple. But what if you actually get an orange because you have sliced it out, right? So the idea here is that you make something smaller, that you reduce the dimension of this material, and it behaves very differently from what you expect the material to do. So this phenomena in physics, we call this as emergent phenomena. Emergence meaning that something is not behaving like the way it would in a bulk material, or there are interactions in the system which makes it behave differently from what the bulk counterpart would do. Okay, so that's what 2D materials are famous for, or that's what makes them special. Now the class of material that I work with are all carbon-based materials. So just to give you a background on what these materials are, so in 3D you're familiar with graphite. So this is just high school physics that you learn about. Graphite has got an arrangement which is, there are these sheets which are stacked in vertical directions, and you have van der Waals interactions between these layers, right? And you have covalent bonds in plane, but you have van der Waals interactions between these layers. So these interactions are not as strong as your ionic or covalent bonds, so you can sort of cleave these layers out, and that's what makes it special. So you can cleave out a layer of graphene, and that makes it a purely 2D material. So this is just one layer of atoms. You can't go smaller than that. So that's the 2D material that we're talking about. Often you will find people call something 2D when it's actually much thicker than what these layers are, right? But here we'll be talking only about the graphene and maybe few layers of graphene. You can also have a carbon nanotube where you fold this graphene back into a tube-like structure, and that's what is shown here. You can also have a 0D analog, which is called as a buckyball, where you have a structure like this, like almost like a football that you probably may have seen. So all these are carbon, varieties, and we'll be focusing on the graphene. Now, just to give you a history, the word, we often call this as lead, right? Pencil lead. So the word came about because of this terminology, which meant lead ore in Latin. This was 16th century, that's when the material was discovered. In 18th century, it was used to write. So that's why it's called as graphite, which means to write in Greek. Now, people soon realized that this does not have any lead content in it, but for some reason the word lead stayed on. So we still call this a pencil lead, but it's purely carbon. It doesn't have any Pb or lead content in it, okay? Now, like I said, this was graphite, so every pencil lead, it's basically a chunk of graphite like this. May not be as ordered like this, you may have crystals in different directions, but that's what it's made of. Now, it's possible that when you write, you leave out a single layer of graphene, because as I said, these are weakly bonded, so it's very easy to cleave these materials out. So if you can do that you can get rid of all the other layers and leave out a single layer, you call that as graphene. And these two gentlemen in 2004, with a very interesting technique, which we'll see in some time, were able to isolate these graphene layers. The physics of graphene was well understood, at least theory-wise, for a very long time, but it was very hard to exfoliate this material and make it in a lab actually. So although a lot of effort had gone into this, it was only in 2004 that this was actually set up in a lab, and since then this has been a very active research field. Okay, and they won the Nobel Prize in 2010. So this is Geim and Novoselov who first isolated this and studied their properties. So now let's talk about how to make this material, right? So the easiest thing that one can do is to take this material and sort of shake it, put it in a solution and chemically exfoliate it. So bring in some atom in between so that these, it's like forcefully getting these layers out, right? So that's one way of doing it, which is called as chemical exfoliation. So you go from graphite to graphene by forcefully taking out these layers and separating them. Another very interesting technique, which was roughly the same time, it's very interesting the history how this material came about. You can see this is 2005 paper. So around the same time there was another group which was trying to do this, and the way they operated was they took an AFM tip, which is like a small cantilever, and they brought this to this, it had some amount of graphite in it. They brought this cantilever onto a wafer and they tried pressing on it. So their idea was that if I press it, maybe a few layers would cleave and be on the surface. And they were able to get these sort of nice looking graphite layers, but they were not single layers of graphene. Okay, so they had a very nice work where they studied the properties as well, but they were slightly thicker, and which is why this group didn't win the Nobel Prize, right? The technique that we commonly use in the lab, which was what was discovered by Novoselov and Geim, it's a very simple technique. So the idea is you take graphite crystal on a scotch tape. So this is like a sellotape, right? Scotch is a particular brand. So you take the sellotape, paste this crystal on it, and you keep pressing this tape with respect to each other. So after a while, you'll sort of thin out this crystal and it will become something like this. Now what you can do is, so this has got still like very large chunks of graphite in there, and you take another clean wafer and you transfer this tape onto it. So this is a wafer, I put this tape on top of this, so you can see the wafer is somewhere here. You rub on it for some time and then you peel out this tape, okay? So you have this wafer after exfoliation. Somebody took a photograph from the lab, that's why you see a flash, but it looks dirty with some pieces on top of it. Now you take it to an optical microscope and view it. So most of the times you may see that there aren't these large pieces of graphite, but if you're lucky enough and you've got good eyes, you might be able to spot a thin layer of graphene over here. So these are graphene, maybe some of them are bilayers, some of them may be trilayers, but they are very thin layers. So looking through an optical microscope, you can see these sort of things, and there are other characterization methods that you can use to figure out if this is actually one layer or two layers and so on. But the process as such is very simple, and this is what won them the Nobel Prize. They were able to isolate the graphene layers using a very simple technique like this. Now, moving forward, the way the field progressed, I told you, right, these are van der Waals materials. So they are held together by weak van der Waals interactions in the z direction. Now, this offers a new type of tool for you to create a material, right? So as material scientists, you often go to a lab, synthesize a material by, from first principles. You take some solution, mix them together. You're like a chemist, right? This is a very different way of coming up with a structure. So what you can do is, you can reduce these materials to a single layer. So this is an atomically thin material, but now you have a lot of materials to choose from. Okay, so graphene was only the beginning. So after graphene, doing the same process, you have a variety of van der Waals materials to choose from. So they can be insulators, semi-metals, semiconductors, metals, all sorts of things, right? You have a very wide variety of materials that you can choose from. So now what you can do is, this is like building blocks, right? So you have these building blocks which are made of, all these different varieties. You can stack them together and create a structure that you want. Okay, so it's just like combining chemicals and creating a compound. Now you can combine these different 2D materials and create a new material. Okay, and this is called as a van der Waals heterostructure, where you take these different 2D layers, bring them together. So in my previous analogy, it's like stacking these fruits together. And what you have, this heterostructure means that you have a structure which is made of different types of materials, and that is going to show you different properties from what you would have imagined for any of these individual layers. So now you have a tool by which you can combine these materials and create devices out of this. I'll briefly tell you about devices in just a bit. But you have a tool whereby you can bring all these materials together, combine them and design devices to suit your requirements. Okay, and why do these materials sit together like this? Again, they are after all combined by, sticking together by van der Waals interactions. So in plane, the bonding is still very strong, but out of plane, these variety of materials that you have put in, they will all have some van der Waals interactions and they will stay together. So they don't break apart into pieces, and you will be able to work with these materials in a lab. Okay, so this, as the history goes, graphene was first isolated, some other semiconducting materials were then found, and a huge variety was found, and then we could combine these materials to create the heterostructures. Now let's look at how to do this. I'll show you, like you might be wondering, how do we take out, if you think about it, it's just a single layer of atoms after all, right? So all these individual stacks that I'm drawing and showing you, they're actually a single layer of, they all form single layer of atoms, right? So it's composed of single layer of atoms. So how do you combine them together? Now this is again, like, most of these techniques that I'm talking to you about are very crude techniques. Now you all have scotch tape at home, you all have graphite pencil. In principle, you can do the same thing, right? You may not have an optical microscope, but the technique is pretty crude. Even here, the technique is very crude, okay? So what you start off with a glass slide. And you put a polymer, doesn't matter what polymer for now. So it's a polymer, it's transparent polymer. And then what you do is, you make this is how it looks. So there's a small polymer hemisphere blob in the center, and you stick it onto an aluminum frame. This is just to hold it. And what you do here is, this is a silicon wafer which has got the 2D flake that you want. It's already exfoliated. Exfoliation is that process that I told you with scotch tape and stuff. So it's mechanically exfoliated onto this wafer. You take this small polymer stamp which is shown here, and what you do is you bring it down together using a setup like this. There's an atomic microscope, there's an optical microscope, and you have that, this thing is hanging, okay? So it's sort of like hanging like this. You look through this microscope and bring it down together, and then the polymer that is here will stick on to the layer of interest that you have. So it's something like this here. There's a silicon wafer. That polymer is brought in contact like this, and then you lift it up, okay? So when you lift it up, this flake of 2D material which was here has now gotten transferred to the polymer. So basically you used it like a sticker, brought it, took the material off the surface. So now your 2D material is on top of the polymer that you have. Okay, now you go ahead and repeat this process. Before that, so this is how it looks. So this was a 2D material that I wanted to pick, and you see this is already in the polymer. This is the polymer. Now what you can do is you can bring this onto another wafer with another 2D material. Okay, so you have to align this, which is why you need the optical microscope. So you bring them together. So you see that particular flake is now put on top of another 2D material here. Okay, so this is a boron nitride flake, which is an insulator, and this is graphene. So this is this long strip is graphene layer, and now what happens is it picks it up as well. So now you see that material has gone from the silicon wafer. It's hanging on the polymer now. You repeat this process, and you can just continue to make whatever stacks you want. So you basically have the polymer, which is like a sticker, bring it and then keep taking the material, whatever ordering you want to do, you can do it. So eventually you have something like this, which you can drop onto another wafer. So you see, this is now dropped onto another silicon wafer, and this is the silicon wafer. The previous image was the polymer again. So now you have taken it. So what you've done is you've manipulated the 2D layer, right? So the 2D layer was on some particular wafer. You took it out from there and put it onto another wafer. So you have this control of playing with these sort of thin materials and making the structure that you want to create. So this is called as van der Waals stacking. Like I said, it's all reliant on the van der Waals interactions that you have. Now, is this the only way to do it? Is this always this crude? No, you can have a better method to create this. It's called as chemical vapor deposition. This is opposite direction, right? There we started off from a 3D material, graphite or other 3D crystals, went down to a 2D material, then created a stack out of it. But here what you do is you start building the 2D layers. So you can create these 2D layers layer by layer by using some chemical processes. As of now, the technology to do this is still in its infancy in terms of heterostructure. Of course, you can do large area graphene growth by using this technique called as chemical vapor deposition, but creating a heterostructure is still very challenging. And the quality of the electronic devices that you create out of this process is a little inferior to the quality that you would get from the process that I told you about. So although the process looks very crude, as of now we have quite a good control on the electronic properties of those materials, and they give you the best devices as of now, which is why many labs focusing on studying the fundamental properties of these materials rely on that in comparison to this. But if you want to have an industrial scale, scaling up and so on, then this sort of large scale techniques become very relevant. So this is also a parallelly a very active field of research. Okay. Now let me talk about, so we now have the material, we want to do something with it, right? So how do you create a device? So now I'll be moving forward to how we make a device out of this material. So if you have any questions in the previous part, yes? Yes.
It depends on the relation between that layers also.
Whether they will stay together, is that what you're asking? Yes. So normally, yeah, so his question for those who didn't hear is, can I just randomly combine materials, or will it depend on something that the choice that I make for these layers? So when you normally grow materials, like the way I showed you, right, there you have a lot of constraints. So you would have to match the lattice constant of these materials. In the sense, what is lattice constant? The distance between the atoms, right? So the repeating units, that's lattice constant. So you have to match the lattice constant, because otherwise there may be strain in the material, right? And the interface may behave little differently. So when you grow materials, you have all sorts of constraints. Now, when you do a van der Waals epitaxy, which is this particular material, this style, you don't have to worry so much about those constraints. So in principle, you can take any 2D material and put it together. What can happen is there may be some local relaxations in the material, right? So you might want to put it in some particular orientation. They may slightly relax so that the lattices are relaxed. But there is no constraint in the process as such. So you can, so what is your background, can I ask?
Means I am currently doing undergraduate in computer science engineering.
Computer science, okay. So you would have heard of semiconductors and band gaps and so on, right? So when you're talking about semiconductors, when you put things together, you can have like two different band gaps which are sandwiched, and there are band alignments and those details that are important. So in principle, you can create a device where you tune, you design a device where you want to have a certain band profile by picking certain 2D materials, right? And that's what sometimes drives us to come up with a choice of materials, and you can follow that. There may be small differences when you actually make the device, but there is nothing prohibiting you from getting that stack, if that was what you were asking.
Yeah, means one more thing, can I just
Yes, sure.
this, as you said, that the layers stick together, it can be because of some electromagnetic also and bonding also, means somewhat you can
You're
say
asking if there are in-plane bond, vertical bonding.
weak bonding or somewhat between that chemical, means
Yeah.
outer electrons bonding or
Yeah, so
somewhat.
if you have dangling bonds and you have like something that's compatible, that can happen. But for instance, the layers that I'm talking about, right, graphene, and you bring in something else like an insulator, boron nitride, there it may not happen. So that may depend on the particular choice. Or if you have like some other species which can, oxidize, or certain reactions can occur, that is possible. Yeah. You can also have oxidation. That is also certain materials are very reactive. So if you bring them together and leave it like exposed to atmosphere, they will oxidize. Right? So those are possible. Yes.
You talked about the emergence phenomena, right?
Yeah.
So you talked about the emergence phenomena, correct?
Yes.
So I didn't understand that emergence phenomena, how it comes into picture in this.
We'll come to it
okay.
towards the end of the talk. I'll discuss that. Yes. There are few techniques to do that. One of the easiest techniques is to do a Raman spectroscopy. If you have heard of what is Raman, that's what C.V. Raman won the Nobel Prize for. So that's an optical measurement, and that gives you certain different signatures for these two layers. Because of the presence of an additional layer, right? So there are these vibrational modes that are slightly different. So that can give you an indication. Or you can do an atomic force microscopy, which is basically you can map out the height of the layers. So if you have a single layer, that will be like something like 0.3 nanometers. But if you have two layers, that you can measure the height to be double of that roughly. There may be a small van der Waals gap. So yeah, so you can map out the height, or you can look at some optical properties. These are two commonly used techniques. There may be more that you can use. Yeah.
Like during exfoliation, you mentioned that if you're lucky, then you'll probably see a similar or a bilateral. So like, are there any specific techniques during exfoliation which will increase the chances of getting a similar, or is it purely?
There are two things to it. One is your ability to view it, like you're viewing it using a mic. Like we do still a very old style way of doing it, but there are labs which have automated this. So you can look at the contrast. It's an optical contrast. So you can look at the contrast and figure out. Your eyes sort of gets tuned to viewing it if you have done it for a while. That's how most of my students do it. But you can use filters to enhance the contrast. Sometimes people have even written codes to, like figure out if the contrast matches with single layer or bilayer. So that's how, when you do it, you figure out. So most of the times you do see, like if you're good at that process, right? So I said it in simple terms, but there's a particular way in which you have to transfer the tape onto the wafer. So if you get good at it, then you will not have those bulk graphite, but rather the chances of getting graphene is more. It's like an experimental optimization. Shall I proceed? Okay. So moving on. So now we have the material. We have to make these devices. So how do you make this device, right? So these are small. So I didn't tell you about the dimension. So this is not to scale, of course. So this sizes that you normally have on the wafer are like 10 to 20 microns. Or maybe even a little more, but tens of microns, okay? And you want to take out electrical contact so that you can measure these devices. So what I'm going to show you is how we do this, and as Akshay already mentioned, you'll have a tour of the SENS facility that we have, and we do all these processes there, okay? That's like our bread and butter for most of the people on campus, experimentalists on campus. So this is a layer which is on a device, on a silicon wafer. So what we can do is we can sort of pattern this structure. So let's say that we have a funny shape that you have, and you know that when you apply Ohm's law, you want something like simple, like rho L by A or something like that, right? You have these geometries which play a role. So if you have a funny shaped structure, of course you can measure resistivity and other properties, and to find out resistance you can measure, but to connect it to resistivity becomes harder. So what we normally do is we pattern this. By patterning, I mean you remove this graphene from certain areas. So you sort of design the device layout that you want. So we design in what is called as a hall bar geometry. This is not to scale, this is just a schematic diagram showing this. So you make it into a nice rectangular geometry with probes coming out. Okay. So that way your length and width and everything is easily measurable. And then you put these electrical contacts, these are gold contacts. This is again not to scale, using some of the tools that we have in sense facility. So these are ohmic contacts to this 2D material. Okay. Now the techniques involved, I'll not go into the depth of it, but you can Google about it if you're interested. Electron beam lithography, etching is to pattern this into some shape that you want, and then you deposit metals on top of it. So these are the 3 techniques that are important to create these devices. Now you might wonder, like I showed you the 2D material that way, but many times what happens is the material that you want to study may be inside a sandwich. Okay. So you can't put contacts from top of it because the material that you want to study is buried inside the surface. So there are 2 ways to do this. One is to drill holes into the surface and then put contact so that it touches what is inside, and otherwise you can have a side contact. And many times we do this side contact. So what I mean by that is, this is a very interesting technique from this paper. This is what is being used currently by world over. So let's say that you have a boron nitride, graphene and a boron nitride. Now this is a typical structure. This kind of structure where graphene is encapsulated within 2 layers of boron nitride. Boron nitride is an insulator. This is a structure that gives you the highest quality electronic devices. Mainly because this graphene would not see any outside residues, polymers or anything else that is needed to do the fabrication process that we are talking about. So this graphene is very clean, and that leads to the highest quality. So if you have a structure like this and you want to create contacts, you can't, this is exactly like this bread and the cheese piece probably which is inside, right? So what you want to do is you will etch this into something like this. So basically cut this bread into 2, and then let's say you have the cheese which is exposed now, right? And then you touch the cheese from the sides. So that is the idea here. So this is your graphene layer. You etch it into some smaller shape so that this graphene is exposed now, and then you touch the graphene from the side. So this technique is what would allow you to pass current into the 2D material which is now sandwiched. Okay. Now to give you an idea of the scale, so this is one of the devices that we had in the lab, and this is where the actual graphene layer is. Now if I zoom into this area, this is how the lithography patterned device looks like. If I further zoom into this area, you would see there is a heterostructure which you see in blue color, and these are yellow things are the contacts that are put on the heterostructure. Now if I zoom in further, you will have some heterostructure like this. This is what I showed you earlier when we picked up multiple layers, right? So you have a heterostructure like this, and inside that basically it's this, right? Multiple 2D layers which are stacked. So eventually what has happened is, now you have drawn electrical contacts from here and it's connected to some pins over here, and now you can measure these devices. Okay. So as you can see, this is very, very small, right? This is a very small device that we're talking about, but eventually we have come up with something that's about 1 or 2 centimeters, like we've connected it to something, right? And the process flow that we follow is you have sample preparation and device fabrication. We have talked about these 2 parts. We do it in a clean room, so that's a clean room in sense. And after this, you have to measure whatever property you want to study. So we use low temperature systems in our lab, but that's particular to my lab. You can measure this at room temperature as well. So this is a low temperature system in my lab. And then you have data which you analyze. Okay, so this is the normal process flow when you're talking about any quantum device, for instance. Okay. Now low temperature and high magnetic field, that's because in my lab, we want to study how these materials behave when they're subjected to very cold temperatures, how the electrons move when they're subjected to cold temperatures and high magnetic fields. So we put this in an arrangement like this. So this is the chip that I showed you in the previous slide, and that goes in, this sits at about 1.5 Kelvin in this particular experimental setup. 300 Kelvin is room temperature, so 1.5 Kelvin is negative, you can calculate that. So, so this is the setup where it goes into the cold environments, and that sits in this unit. So basically this rod like structure goes into this jar. It's like a flask basically. It's a cold system, which is why it's isolated from the environment. And we study this. Looks like an octopus in this particular image. There are lots of pumps and other things. Okay. So now let's talk about some physics. Okay, I've told you about the how we create the samples. Now let's talk about some physics. I'll keep it very basic, but if you have questions, please feel to stop. You would have seen this in school: metal, semiconductors, insulators. Metals have an overlapping band, semiconductors have band gap, and if the band gap is very large, you call that an insulator. So this is, in terms of physics, so this is energy as a function of distance normally that's plotted. Even the axis is very vague when you learn this, but as you go, I'm hoping there are more, there may be engineers here who may understand this diagram, but if you don't understand, that's fine too. This is a band structure of silicon. So these bands are now plotted as E versus K, or momentum. And the important thing to notice here is that this is the valence and this is the conduction band for silicon. It's an indirect band gap material. So you have a parabolic band normally. So silicon or any other material that you talk about has a parabolic dispersion. So E as a function of K, or the momentum, it goes as E proportional to K square. In case of graphene, if you plot energy versus K, this is now plotted as Kx, Ky, you see that the band structure is where your Fermi level is, that's linear. Okay, so that's the main distinction that you can easily draw between silicon and graphene. And if you zoom in there, it basically looks like this, right? Instead of this parabolic shape, you have a linear dispersion in E versus K. That's the conduction band, and this is a valence band, and they touch each other. So it's not really, there's no band gap as such, they touch each other. Okay, now the physics of single layer graphene is interesting because it has got what is called as a honeycomb lattice. So it's got these atoms arranged in a hexagonal fashion. And now this arrangement of atoms, that's what gives its beautiful band structure, which is very different from all these conventional semiconductors that I talked to you about. So what it means for an electron is, the electron that is sitting, so basically the valence band is fully filled and the conduction band is empty, that's what you normally say, and that's where my Fermi level is. So this electron sees a linear band structure, and that's what leads to all its interesting properties. In terms of measurements that I told you about, if you measure the resistivity as a function of gate voltage, what I mean by gate voltage is you can manipulate the charge carriers in the system. So if you apply a positive gate voltage, what you're doing is you're populating the conduction band. So you have electrons in your system, or your charge carriers are basically electrons. Now, in case of silicon, you can't change the carriers. You do it by doping, right? You put in boron or whatever dopants you put will determine whether it is N-type or P-type. The advantage of using graphene is that just by simply applying a gate voltage, you can change from electrons to holes. It's just this special band structure that it has where it is touching. With a gate voltage, you can manipulate this. So if you apply a negative gate voltage, you have depopulated the valence band, which means that you have populated it with holes. Okay, so you can go from holes to electrons, and then between that you access this Dirac point, or the point where it is just crossing each other. So at that point there are no carriers. So that's why one way to understand this large peak is that there are no carriers here. Here you have electrons, here you have holes. In both cases the resistivity comes down. Alright, now let's talk about bilayer graphene. So bilayer graphene is similar. So you take one layer of graphene and put another layer of graphene on top of it. You would have learned this again in school as A-B stacking. Okay, so there is A atom and B atom which sits on top of it. So that's what you see here, A-B stacking, and it again has a very similar band structure. So it has got all these what are called as K and K prime points. I'll not go into the depth of it, but you feel free to ask me after the talk. So you have again a parabolic sort of dispersion. It's not linear anymore, but they're again touching each other. Okay, in this picture it's not very clear because I think they've opened a small band gap, but it touches each other. So you again get a similar looking resistivity curve where you can go from electrons to holes, okay, by applying a gate voltage. So now the interesting thing about graphene is you have a system which you can tailor to be an N-dope system or a P-dope system by simply using a gate voltage. Okay. Now bilayer graphene is also interesting because in bilayer graphene, if you apply an electric field, so you take a bilayer graphene and you put an electric field in a perpendicular direction, what happens is it opens up a band gap. Now band gaps are important because if you're talking about creating a device out of this, you want the device to turn off. which means you need to have a band gap. So this was an important discovery, that putting in a displacement field or an electric field in the perpendicular direction opens up a band gap in bilayer graphene. In single layer graphene, you don't have that. So many of the electronic devices that you may read about, even for quantum computing purposes, use a bilayer graphene. Okay. Now, what is special about this? There are a lot of properties. I've just listed 2 properties of graphene which are very unconventional. One of them is this quantum Hall effect. So for those of you who are not familiar with quantum Hall effect, this is a special case when you apply a perpendicular magnetic field, you have a quantized resistance. So this Rxy that you have, it's quantized in some number of h upon e squared. So these are fundamental constants, h, Planck's constant, and electronic charge, and you have resistance in your system which is now quantized. And this has been known before in other two-dimensional systems. Graphene shows very unconventional quantum Hall effect. It also shows a phenomena called as Klein tunneling, where even if you have a barrier, you have a complete transmission that's possible. In a regular system, you will have some sort of decay like this. So what I wanted to show from this slide without going to details is that graphene shows a lot of exotic physics, right? There are these sort of phenomena which are seen only in graphene and not in other materials such as silicon. And it is also projected to have a lot of applications in various things ranging from energy, environmental, biomedical, and so on. Quantum technologies is not really listed here. I'll tell you a little bit about that towards the end. Okay, now I started off with magic in 2D land. So let me go to the magic part of it now. Okay, so we spoke about single layers of graphene and bilayers of graphene. Now you can ask this question that, I have the flexibility to take 2 layers of graphene and put them together. If I do that, so it's not that you exfoliated the graphene and you found that there was a 2-layer graphene. That is always going to be in the Bernal bilayer or A-B stacking that I showed you earlier, and it will have that band structure. But what if I take 2 separate layers of graphene and bring them together and put it together? Will it behave like the Bernal graphene? The answer is no, because you have what is called as a twisted system. So depending on how you combine these 2 layers together, it can have any funny structure like this, right? So as I keep moving it, you would see that, let me go back and show you this again. You would see there is some periodic pattern that emerges in the system, larger periodicity that emerges as you keep rotating the system. This is called as a moiré pattern. You would see these moiré patterns in various things. Sometimes on TV screens you could see this earlier. So if you have 2 periodic structures and you overlay these 2 structures together, you can have a moiré pattern if you rotate it, or if the pitch of these 2 things are slightly different. So here you have 2 lines which are like overlaid, and you see this larger structure that appears, right? Here again, set of square lattice which is rotated now, and you see this picture. So similarly, if you take graphene and boron nitride, they have very similar lattice constant but not exact. So if you place a graphene exactly no rotation but place it on top of each other, you will have a moiré pattern like this. Similarly, you take 2 graphene layers and rotate them with respect to each other. Again, you will have a moiré pattern like this, which is what I showed you earlier. So this structure, what it means is that the very simple way to think about it is, how do you get a band structure? You get a band structure because you had a particular crystal structure from where you started off and you found out how the band structure is. Now what is happening is you have a larger crystal structure that's emerging in this because of the twist, right? So this crystal structure means that in real space, this crystal structure means that you will have a band structure which is very different, okay? And the importance of this band structure is that these band structures, as you rotate this material from 2 degrees close to 1 degree, your valence and conduction bands have now collapsed in energy space. So earlier you had a dispersion which I showed you as linear or parabolic, which had some energy width, right? It looked something like this. But as you made these structures smaller and twist angles smaller and smaller, what you see is this is collapsed into what is called as a flat band, okay? Now this is very interesting. So what I am telling you is that whatever valence band or conduction band electrons were there earlier, they have now come about in a very small energy interval, which means that your Coulomb energy is very large in these systems, okay? Or another way to think about it is you give it a small amount of energy and you have a lot of electrons which are populated because this entire band is available. Earlier you had to give maybe a few eV of energy for you to populate the whole band. But in this system, by applying a small gate voltage to your system, you will have a lot of electrons that you can populate into your band. That means there are a lot of electrons, there's a lot of interaction, and the physics that you will have will not be similar to what you had seen earlier, Okay. Now this happens, this sort of band flattening, this is written in terms of velocity, but imagine that this is the same thing. This happens only at certain angles, close to what is shown. This is not given in terms of angle, but the angles are listed here. It happens only for certain angles, and they are called as magic angles. Okay. So the idea is that if you are at the magic angle, if you rotated your system to that particular magic angle, then you have a system which is highly correlated, where the electrons interact very strongly. Okay. This was a huge discovery in 2018. This is what is called as AP's, it's a particular conference which is very famous, and the room was overflowing and they had to put a screen outside because this was such a big discovery. And the discovery was big because it showed two things. Earlier in the previous graph when I showed you resistance as a function of gate voltage. This is the same graph, but they used conductance as a function of carrier density. So if I were to convert my previous graph, my resistivity peak would be a dip. Okay, so take it to be that way. So in graphene, you would have had a single dip in conductance as a function of density. Sorry. So this is my charge neutrality point. Now what you see here is there are these additional dips at when the half of the valence band is filled or conduction band is filled, and when that valence or conduction band is fully filled. So there are two things here. You can access the band fully, and there are these additional insulating states that appear. So what we're talking about is you have electrons in a band and you fill the band only up to half of the band. So for people who are familiar with it, if you have a half filled band, it's normally a metal because you have an additional state which is just beside it, which can take the electrons. In this case, they found that they have an insulating states, and these insulating states are signatures of emergent phases, which you were asking about. So that's one thing. Just to explain that particular phenomena, so you have metal, you have semi-metals, and you have insulators. So you can redraw this diagram something like this. So for metals, you have the Fermi level in between the band. So if you give a little bit of energy, it can take that energy and go to another state which is right here. In case of semi-metals, these conduction and valence band touch each other. In case of band insulators, your electrons, your Fermi level is going to be here. This is the valence and the conduction band, right? Now, in case of normal band insulators, this is what you expect, that your Fermi level lies inside the gap. But you can have a situation where you have correlated insulators. Because of correlations, what happens is that this particular band now splits into two, and you can have this band gap which is present at half filling. So this half filled structure now separates into two, and your Fermi level lies inside a gap. You would normally think that it's lying inside the this particular band and it should be a metal, but at half filling it turns out to be an insulator. So these are called as correlated insulators. They have a lot of applications in superconductivity, and the wide variety of materials show this. Now the interesting part is that graphene also shows this. Graphene, which is a very simple material, also has a correlated phenomena that is coming in only because you have twisted this material with respect to another simple layer, and that doesn't behave like graphene anymore. The band structure has completely changed. Okay, that was not all. The most important discovery was that this also shows superconductivity. Now a material that shows superconductivity is usually like something that's very sought after. So this particular material shows superconductivity. It's a metal when it is at some higher temperature. It's an insulator. It's called as MOT here, but it's basically that insulating state that I talked to you about. So you have a material now where you can change from an insulator to a metal to a superconductor simply by changing the number of electrons, or simply by applying a gate. If you are familiar with transistor, applying a gate is no big deal, right? So simply by applying a gate, you can go from a metal to a semi-metal to a superconductor to an insulator. So you have a lot of tunability. Now what does this offer you? So if you are an engineer, normally if you want to design a device, you need 100 things to combine it together, right? Here you have a material where you can electrostatically change the material's property and create devices that you want. Okay, so that's why this material is very interesting. I'll skip this for the lack of time. So just to summarize, you have this twisted bilayer graphene which I showed you. I told you about superconductivity, and I told you about insulators. But there are a lot of other phases of matter which are also very interesting. I'll just flash these ideas to you so that it's just familiar to you. These words are just familiar to you. It has this property called as orbital ferromagnetism. Now what is orbital ferromagnetism? You're probably familiar with spin ferromagnets. I think the next talk also talks about magnetic materials. So when you talk about a normal magnet, iron or any magnet, you have spins which are aligned in a particular direction, right? Now an electron can possess spin, but it also has an orbital degree of freedom, it circles, right? There is an orbital degree of freedom. Now that orbital degree of freedom may also align, which means it can circle in this direction or all the electrons can circle in the opposite direction. Now that can also lead to a ferromagnet, which is called an orbital ferromagnet. Every material has these 2 degrees of freedom, just that this, this particular magnetization is very small. The quantum of this magnet, or like if you quantify this magnetization, it's too small to detect. In twisted bilayer graphene, it is very strong, and we also have a paper, I haven't even put that reference, but which works, so you are able to realize an alternate form of magnetism, okay. This is also a very interesting effect. So if you take any material, you say that if I heat it, it will go from solid to liquid, right? That's your normal understanding. Here, if you heat it, the electrons freeze, okay. So the idea is this, so if you're here, as the temperature is increased, the electrons start to align in some particular manner. This particular effect is called as Pomeranchuk effect. If you're interested, again, please, you can go through the literature on this available online. There's also this idea of pneumaticity. You may probably have heard of pneumaticity. Pneumaticity is very common in case of liquid crystal displays. So you have a particular orientation to your small crystallites, and they're called as pneumatic. So this is a crystalline solid, whereas here, you see this orientation that you see here. The electrons in this material also show this particular property, which is pneumaticity. Now, one of our own works, this work is from my group, where we discovered charge density waves. Now, charge density waves, one way to think about it is, so if you have a lattice, this is the twisted bilayer graphene at 1.1 degree, where I showed you these patterns earlier, right, which had this larger crystal structure. Now, imagine that for some reason, initially all of them were similar, which is what is marked as red here, but for some reason you have a difference between this site and this site, okay. So what happens is now you will have a larger periodicity. So this was my original unit which was repeating, now you have a larger unit which is repeating, okay. Now what this translates to is that if you had a uniform electron density, then your ions are sort of uniformly spaced and the electron density is also very uniform. But for some reason you make all these ions bunch together. Then what happens is your electron density gets modulated. This is what is called as a charge density wave. We were able to realize a charge density wave in this particular system. Again, this is also an emergent phenomena, not seen in single layers, but seen in multiple layers. Gone into, I just wanted to flash these phenomena to you so that you're aware of what are the opportunities that this material offers to you. So there are lots of phases that can be stabilized by changing your gate voltages or by changing the environment. So this particular thing we achieved by changing the dielectric environment of the material, okay. So now this is not only confined to twisted bilayer graphene now, there are lots of other states, other materials. You can twist 2 bilayers of graphene. So instead of taking 2 single layers of graphene and twisting them, you can take 2 Bernal or AB stacked bilayers of graphene and twist them. Again, that shows very similar but slightly different properties, and a whole bunch of these materials. Mono bilayer, a single layer of graphene with another bilayer of graphene, 3 layers of graphene, and this is another material which is called as an ABC trilayer, so it's like a stacking that's present, and a variety. Even Bernal bilayer graphene also shows this emergent phenomena. So once people realized that having this flat band leads to all these properties, now you can also imagine Bernal bilayer graphene has a parabolic dispersion. So you have that bottom of the band which is also flat, right? So even there you can realize some of these emergent properties. And this is where we are right now, just to show you the wealth of phenomena that you have here. Twisted bilayer graphene is when it started off. Right now we are moving forward and multiplying the number of layers that you have. And these are the properties that have been realized in these materials, and it is always increasing. It's like a funnel, right? That's because just to show you that the number of properties and the number of systems that are coming in this broad spectra, that's increasing. It's only like 5 years or 6 years now that we've been studying this, and lots of phases that are stabilized. So how does it connect to quantum devices, right? You see two things which are important here, insulators and superconductors. So that becomes a natural platform to realize some parts of superconducting qubits, Josephson junctions, squids. Whether they'll ever become a superconducting qubit is difficult to predict right now, but the fact that you have these controllable states make it very usable as these components which may be useful for many of the quantum devices. That is one part of the story, right? Second is semiconductor qubits. So see, you never have a system which is both semiconducting and superconducting normally. So you either talk about a system as useful as a semiconductor qubit or a superconductor qubit. Here you have a system where you can transition between these two. So it's also useful to generate quantum dots with them, which can be a building block for semiconductor qubits. So these are two aspects in the using these two properties. Now, if you look at the other properties, there is ferromagnetism and there's Chern insulators. I did not talk about this, but these two ideas are closely related to what are called as topological qubits. This is still a fairly evolving field. It's not been demonstrated yet, but these are the building blocks which will help you realize a topological qubit. So this particular material possesses all these interesting properties, which may become useful in the next generation of devices that we can think about. And where are we right now? Like, you should remember this material was first studied only in 2018. So we have the know-how of only about 5 to 6 years. And already, there are two papers which talk about Josephson junctions in magic angle bilayer graphene, where you can probably imagine. So what is a Josephson junction? For people who are not familiar with it, these are building blocks for superconducting qubits, and what you need is basically a superconductor insulator superconductor junction, right? So normally if you want to create such a junction, you would need to take a superconductor, put some insulator, then again put another superconductor, right? Now with this material, what you have is, you can change the same, you have just one twisted bilayer graphene, but one part of it you can make it superconductor, beside that you can make it into an insulator, again you can make it into a superconductor, all by electrostatic control, by applying gates. So that's what is shown here. With a gate control, they were able to define this superconductor insulator superconductor junction. And not just that, you can even make that insulator into a semi-metal, or like a proper insulator, like a correlated insulator or a band insulator. There's a lot of flexibility available to you. The next one is squid. So you start from Josephson junction. The next thing that you go to is a squid. Squid has got two Josephson junctions in a loop-like structure, and this is what forms the building block for many of these superconducting circuits, and that was also realized. And if you look at the title, it says a tunable monolithic squid. What is meant by monolithic is this idea that I told you about, that monolithic basically means carved from a single stone. Okay, so this is carved from a single material. You don't need multiple materials to do this. The same material can act as insulators and superconductors, and that's what is used to generate a squid. So these are proof of concept demonstrations right now. There's a long way to go to actually make devices. And in comparison, the other counterpart that we have is bilayer graphene. And where does bilayer graphene stand right now? So this is a very recent announcement. Both of this are June 2023. This is just this month, where Intel announced the release of their 12-qubit silicon chip. So these are silicon germanium technology, where it is 12 qubit right now. Whereas in case of bilayer graphene, which is the material that's been studied for a while for creating qubits, this is where we are. The qubits are not yet there, but there have been a lot of properties. This is the latest report where they show electron hole symmetry. So basically you can tune it to be an electron and hole which are equal in sizes in terms of their charges and so on. So that is what has been demonstrated in bilayer graphene. So bilayer graphene itself is not up to mark with silicon yet, but it has lots of advantages which silicon doesn't have, right? This sort of electron hole symmetry, you can't see it in silicon because you can't have a gate control to go from both electrons and holes. So there are certain advantages to bilayer graphene, and twisted bilayer graphene is just the last bit. So I would end my talk. I have not put a lot of acknowledgements, but I can't avoid these people. This is my lab group. It's not the full group. This is only photo that I had where, whatever we do is because of them. Yeah, thank you. I'll take questions. I'll probably leave it like this.
So that recently I was reading that paper that electron in the graphene can directly interact with water molecules.
Okay.
Yeah, so I was just wondering, this is the same thing as electrons is freezing and this?
Oh, no. I didn't really mean that. So that's just a, that was a popular science article where they use the word freeze. What is meant is that normally when you talk about, let's say, ice and water, right? The idea there is that you have larger disorder in the liquid phase and smaller disorder in the solid phase, right? So there's an entropy, thermodynamics would want you to increase entropy. So there's an entropy, not conservation, but there's an entropy related argument that you can give in terms of why it will go from a solid phase to a liquid phase, right? So that's where the freeze word is. So that is analogy. So here also, it's opposite. So from what you would think, like a disordered state to an ordered state, there's an opposite kind of transition. That's what it means. So probably what you're talking about is something else. Maybe it's something related to water purification. Is that what you were?
They published like what these electrons in this graphene, they are directly interacting with water molecules, a push-pull effect they are talking about.
Okay, so that's probably a different effect, nothing to do with this.
I think so. Yeah, another question is like how we use this dark voltage if we are using graphene for sensing purpose. Like how this gas sensing changes this dark points, or the voltage at dark points.
Yeah, so it's something related to what he was asking earlier, that if you have external molecules, there may be charge transfers. Exact phenomena will depend on what molecule you're using and what material you're using as well, but that's the idea, that something's changed, there's some electron transfer, or maybe even strain can change things. So those will depend on details, but that's what is used as a detection mechanism.
And this twisting will affect the Dirac voltage, right? For if we are using this device for sensing things.
When you say Dirac voltage, I'm assuming that you're asking whether it's zero voltage, will you get, is that what you're asking? Yeah, so that will depend on the Dirac point, doping in the system. So if you have no doping in the system, your Fermi level will be exactly at that crossing of valence and conduction band. Now that will always be true for both twisted bilayer graphene as well as the regular graphene. Okay, so your Fermi level will be there. So if you have some doping which is present because of something else, like you have added some polymer and that causes some doping, then your Dirac point will shift, and that can happen for both twisted bilayer graphene and regular graphene. So what is difference is the profile that happens after that. When you dope it into electrons or dope it into holes, then you're accessing the bands, right? The bands in the material. So those band structures are different for the two materials, but the Fermi level position will still be at the point where these valence and conduction bands cross. All of them fall in this broad semi-metallic category. So that is going to be seen.
Thank you. Thank you very much.
If we make Josephson junctions out of the bilayer graphene, so like you said that the band structure is little bit different. It has a linear one as compared to a parabolic one. But to make like a qubit, when we use like a Josephson junction, we need a particular band structure which is like parabolic, which has energy levels which will simulate the qubit, right? So it will generate exactly same one, or will it be different?
So you are asking about superconducting qubits, I suppose, right? Or semiconducting.
If we make for example Josephson junction out of this bilayer graphene.
So that Josephson junction is right now made with aluminum, right? Normally it's aluminum oxide, and yeah. So here the material will vary, but the levels that you're talking about, that comes in because of this LC circuitry that you have, right? That's the that model will still remain the same. You're only changing the material that you have, which changes the complexity in some form, right? So if you want to combine and you want to have multiple qubits close by, and if you can realize a large area, then you have other advantages. But those energy levels that you're talking about, that's a different idea of the oscillator circuits that's beside. So that remains. Only the material is changing.
Exactly, we will able to generate same.
That's the hope. Yeah. So changing a material will not change the physics of the oscillators there, right? So that's the idea.
Ma'am, as I was asking on the emergent phenomena. Yeah, emergent phenomena. So what I understand from the emergent phenomena, let's say we have a system. I mean, single component, what dynamic it shows is different. But if you have multiple components and combine it, it shows something different behavior.
Yeah.
So that's kind of emergent phenomena. But I have not understood here what kind of emergent phenomena.
So the way to think about it is, there are two ways to think about it. When we talk in condensed matter physics, people talk about it. So basically, you have a lot of electrons that are put together, right? So an electron now doesn't behave like a single electron. Or the band structure that I've shown you, that is all calculated for single electrons, right? And I showed you a flattened conduction and valence band, but that doesn't tell you why there should be a band gap at half the band.
Okay.
Correct? So single particle pictures like this fail. And now you have to consider all the electron-electron interactions that are there in the problem to understand the properties. So many of the properties that this shows cannot be explained by band structure.
Okay.
So that's where the emergence.
Yeah, understood. Thank you.
Yeah, it's a collective behavior. So Sorry, related to what? They are all collective phenomena. The surface plasmon resonance in these materials have not been studied as of now, as far as I understand. So yeah.
Yeah, ma'am. And thanks for this wonderful lecture on this. Here, what I didn't understand here is when you twist the bilayer graphene and you are considering only the place where a specific pattern is seen, like moiré pattern, or you'll be considering the whole sheet of that. Or
Yeah, so the idea is that you take two sheets and you rotate it, and the entire sheet has the moiré pattern. So you may have some, like if I combine these two, then you can see this diamond shape is where the moiré is, and these are individual layers, right? That's what you're asking, right? So what we normally do is if you measure only here, then it will behave like a single layer graphene. Only in between, if you put electrodes in between and do it, you will have a this emerge. So if you take the external parts which are single layer graphene, they will behave like single layer graphene.
even in the zone where the two layers are like
So where the two
matching?
layers are touching each other, it
Yeah.
no longer behaves like single layer graphene.
Okay.
So it doesn't matter whether you put contact on top or you put contact on bottom.
Yeah.
They are now a single entity. So
Okay.
the electrons, so when they come in from the single layer, that's like a single layer graphene. But when it enters into this, it's a combined system.
Even the atoms or molecules need not to be aligned in a line there.
They are not, right? They
Yeah,
are twisted,
right,
no?
right.
So they are not aligned like the way you normally think. And
Yeah.
that's what leads to this moiré pattern.
Yeah, fine. And it's a kind of premature question maybe. And how hard is it to industrialize these things?
This is very, very, so that's why I showed you this, just to give you perspective where we stand. We're very far away from that. Even bilayer graphene, I think the bilayer graphene quantum dots have been studied for more than 10 years now. And that's where we stand. We still don't have a qubit.
Yeah.
But there are advantages, and we don't normally chase in terms of that, right? We try to understand whether this is usable or not. So it's far away from where silicon also doesn't stand in with respect to superconducting qubit. This is far off, right?
Yeah.
This is way away, and we are even further away.
Thank you.
Yes.
Ma'am, one question is, as you said that that magic angle of the two layers at 1.1 degree angle or what, it acts as a insulator also and superconductor also. So does it depend on the angle or the temperature?
Both. So if you have, I would say, okay, let me be clear. So with respect to the angle, what it does is basically changes the band structure, right? So it can make the bands really flat, or it can make the bands like have some dispersion. So if you want to see many of these correlated phenomena, you have to stay in that very close to 1.1 degrees. This is only the case of twisted bilayer graphene. When you have other systems like twisted double bilayer graphene or 4 layers of graphene or whatever, then there are certain changes to this. It's not 1.1 degree, maybe some other degree. And also you can tune it with respect to some electric field and so on. Okay, so there are subtle changes like that, but the angle is very crucial for twisted bilayer graphene. That's because the band structure becomes flat only around that region. So what you should think of rather than the angle is what is the band structure. Okay, so that's one thing. A second thing that you asked is whether temperature will control this. So now what temperature does is, let's say that you have some gap that you have opened, and the temperature is higher than that, or the KBT value is higher than that. Then of course this gap won't be visible, right? You will be able to cross the gap. So that way temperature can play a role.
So means I'm not sure, but when I heard about this magic angle in long back, I thought that this was a superconductor which can stay in a superconducting state at a room temperature also. So is it
No,
no?
This is currently superconducting at 2 Kelvin or so.
Yeah.
Yeah.
It,
That's different. That's not on this material. That's a high pressure, and so that's a different problem
and
altogether.
one more question, as you said about that patterns between the tunnel, more
Moiré patterns?
Moiré patterns. It's because of, as you said, that when it touch, means there is a less gap between the
Moiré
layers.
patterns occur for any structure. It's not even for graphene. If you take any, you can actually draw this. If you print some lines on a transparency, 2 transparencies, and rotate it, you'll see these nice patterns.
Yeah.
So this is seen in silk cloth sometimes. Any structure which has got lattice.
Yeah, that was that is visible in the graphene, as you said.
Correct.
Then is it visible because of because of that electronic waves interacting of both the layers
No, I mean, I would put it this way, that you get the moiré pattern because your lattice is now rotated, right?
Yeah.
So that's the reason you see the moiré pattern. So if you are taking some experiment like an STM, are you familiar with STM? So it's like a scanning tunneling, or a TEM, you will be able to find out this repeated unit, that there's a larger lattice structure to it. So that is the atoms, right? We're not talking about electrons yet. Now, for an electron, what happens is, an electron that's normally moving through a material will see this lattice. There's some potential to this that it will see. In addition to that, it will also see now a moiré potential, because there's this additional potential that's coming up because of the moiré. And that's what modifies the behavior of the electron. So there are two things to it. Electrons are separate. This is like a physical thing that you see when you have two lattices. Okay? Yes.
Ma'am.
Okay, go on. You have the mic. You can give it to him after your question.
So I was going through the growth in the number of qubit silicon chips. So in October of 2022, we had 6 qubit silicon chips, and now it's 12. So how do you can you comment on like the relative growth? Like for example, in electronics, we've got something like Moore's law. So is it too early to come up with such a prediction?
So I'm not an industry person, probably not the right person to answer this question, but what I hear from industry colleagues is they are going to scale up faster than Moore's law. I think Apurva probably would. Yeah. It's going to be faster than Moore's law, at least for some of the devices, is the expectation. Right?
Our answer is very short.
Okay, sorry, I'm not the right person to take this question. Yeah,
Thank you, ma'am.
yeah, you have a question there.
Like I was asking, you mentioned when we apply a positive gate voltage to that AB stacked graphene, bilayer graphene, then we have an N dope type and a negative voltage P dope type. So, and you also mentioned on a perpendicular electric field we get a band gap. So I mean, the way I'm visualizing it, I don't know, I think I'm wrong, that gate voltage and isn't like gate voltage and perpendicular electric field the same thing? Like
Yeah. So when you apply a normal gate voltage, you do have some bit of electric field as well, but that's not sufficient to open a band gap. So normally when you want to open a band gap, you will have 2 gates, so that there is a proper electric field setup in the problem. Now you can come up with an equation where you have a top gate voltage, back gate voltage, and some capacitors, top gate capacitance and bottom gate capacitance. And what you will see is that the charge carrier density will depend on the two of them, plus like some capacitance times voltage plus some other capacitance times voltage. So that will determine what is the charge carrier density, and the displacement field will be the negative, minus Vt minus Vb sort of thing. So basically you will, if you apply gate voltages, you can change both charge carrier density and the electric field in the problem. And you can work with such a system that you can keep either the N constant or the electric field constant and then study it. So when I said that it opens up a band gap, if you only have one gate, you have an electric field, but that's not strong enough to open the band gap. You will need an opposite electric field as well from the other side. Yeah.
thank you.
Hi, thank you for the lecture. My background is computer science, so this is a very naive question. So what part of all this apparatus is qubit? Which is
what
qubit?
I showed you about so that's what I was trying to convey with this part, that we don't have a qubit even in bilayer graphene yet, right? But the hope is that, so the way silicon qubits work is you work with quantum dots, right? So there are a lot of advantages to using graphene quantum dots. So that's still in the research phase, and the current, the latest advance is that you can have an electron and hole. You could tune the densities on this the quantum dots using gates slightly differently from what is possible with silicon. So this will be a parallel field, I would say, which is still in its infancy.
Okay, would it be like a whole, the sandwich that you showed? Will it be the whole as one qubit that would work, or you will have other?
You can define. So when you talk about these, right? So what is shown in this diagram? These are gates here, and you probably have like a qubit which is defined. There are multiple quantum dots defined here, which can in principle act as a single qubit, right? But that's not demonstrated yet. But the idea is you have a large enough 2D material, and then you gate define these quantum dots, which can in principle function as a qubit.
Okay.
we are approaching the time limit. Sorry, if you have any questions, you can meet Chandni ma'am later as well. So thank you for such a wonderful and inspiring talk. It was quite an inspiring talk. Yeah, I'd like to give a token of appreciation to Chandni ma'am for such a wonderful and inspiring talk. Yeah, thanks.
Okay. Okay, thank you. Thank you.